Ladies and gentlemen, welcome to Late Night Radio with Freeman Jack. We'll be taking you into the late hours, way into the late hours, and bending your mind.
You have meddled with the primal forces of nature, Mr. Beale, and I won't have it! Is that clear? Is that clear? You think you merely stopped a business deal? That is not the case.
Good evening, ladies and gentlemen. This is Freeman Jack on People's Internet Radio for the Open Omniversity. The Omniversity is open. It's good to be back at a live mic. I'm terribly sorry for the requirement to resort to podcasts the last few weeks. My internet appeared to be irreparably slow. Took them 4 months to 4 weeks to fix it, and halfway through that, my broadcast system refused to accept microphone inputs for some bizarre reason, which took several weeks to fix. So back at a live mic. Got an incredibly hectic show for you lined up tonight. I'm going to take you real deep. Title of tonight's show is Quantum Mechanics or the Conservation of Weirdness, which I should have looked up whose quote that was, but that was one of the quantum key sort of formulators of quantum mechanics. Described quantum mechanics as being the law of the conservation of weirdness. Like I say, very hectic show to get through tonight. Just barely going to have enough time to get it all in by 3 o'clock, so want to get on. And probably the easiest way of getting the subject covered is to, as usual, refer to the best voices, the best minds on the subject. A lot of tonight's subjects will be actually covered by the scientists themselves. Fortunately, amongst the quantum physicists, a lot of them are quite live wires, so not too torturous to listen to. We're starting out with Richard Feynman, he of the Feynman diagram model of quantum mechanics that has been the single most accurate predictive model ever known to science, predictive to phenomenal levels of accuracy. I suppose just as a quick breaking you in, I don't think you're going to hear it in this section, but you'll hear a lot of the speakers tonight talking in powers of 10. You will hear 10 to the minus and 10 to the. Essentially, if you understand something like the square of something, so the square of 2 is 2 times 2, which is obviously 4, or if it's the cube of something, 2 to the power of 3 is 2 times 2 times 2, which is obviously 6. Well, when you get to powers of 10, essentially when you hear something referred to as 10 to the number that is stated after that will be the number of zeros before the first digit. In the case of 10 to the minus, then you can count those as digits after the decimal place. So if it's 10 to the minus 9, then that would be 1 billionth. So lots of noughts after a decimal place. So very small numbers indeed, and certainly some of these accuracies are just phenomenal. Anyway, must press on. Richard Feynman. This is just a little. I'm going to try and lead you by the hand as much as possible through this subject. It's an incredibly complex subject, but I think I've got some really clear speakers on the subject to hopefully clarify the whys, the whens, the what-fors of the quantum model, shall we say. This is a preamble to the digital virtual holographic stuff, which I'll be replaying in the next couple of weeks. Anyway, Richard Feynman, fine.
If you get hold of 2 magnets and you push them, you can feel this pushing between them. Turn it around the other way and they slam together. Now, what is it, the feeling between those 2 magnets?
What do you mean, what's the feeling between the 2 magnets?
There's something there, isn't there? I mean, the sensation is that there's something there when you push these 2 magnets together.
Listen to my question. What is the meaning when you say that there's a feeling? Of course you feel it. Now, what do you want to know?
What I want to know is what's going on between these two bits of metal.
Magnets repel each other.
And well, then what does that mean, or why are they doing that, or how are they doing it?
You're asking.
I must say, I think that's a perfectly reasonable question.
Of course,
it's
it's an excellent question. Okay. But the problem that you're asking, you see, when you ask why something happens, How does a person answer why something happens? For example, Aunt Minnie is in a hospital. Why? Because she went out and she slipped on the ice and broke her hip. That satisfies people. It satisfies, but it wouldn't satisfy someone who came from another planet, knew nothing about things. First, you should understand why, when you break your hip, do you go to the hospital? How do you get to the hospital when the hip was broken? Well, because her husband, seeing that she had the hip was broken, called the hospital up and sent somebody to get her. All that is understood by people. Now, when you explain a why, you have to be in some framework that you allow something to be true. Otherwise, you're perpetually asking why. Why did the husband call up the hospital? Because husband is interested in his wife's welfare. Not always. Some husbands aren't interested in their wife's welfare when they're drunk and they're angry. And so you begin to get a very interesting understanding of the world and all its complications. In order to if you try to follow anything up, you go deeper and deeper in various directions. If, for example, you could go, why did she slip on the ice? Well, ice is slippery. Everybody knows that, no problem. But you ask, why is ice slippery? That's kind of curious. Ice is extremely slippery. It's very interesting. You say, how does it work? You could either say, I'm satisfied that you've answered me, ice is slippery, that explains it. Or you could go on and say, why is ice slippery? And then you're involved with something, because there aren't many things as slippery as ice. It's very hard to get. Greasy stuff, but that's sort of wet and slimy. But a solid that's so slippery, because it is in the case of ice that when you stand on it, they say, momentarily the pressure melts the ice a little bit, so you got a sort of instantaneous water surface on which you're slipping. Why on ice and not on other things? Because ice expands water expands when it freezes, so the pressure tries to undo the expansion and melts it. It's capable of melting it. But other substances contract when they're freezing, and when you push them, they're just satisfied to be solid. Why does water expand when it freezes and other substances don't expand when they freeze? All right? I'm not answering your question, but I'm telling you how difficult a why question is. You have to know what it is that you're permitted to understand and allowed to be understood and known, and what it is you're not. You'll notice in this example that the more I ask why, it gets interesting after all. That's my idea, that the deeper a thing is, the more interesting it is. And we could even go further and say, why did she fall down when she slipped? That has to do with gravity, involved in all the planets and everything else. Never mind. It goes on and on. Now, when you ask, for example, why two magnets repel, there are many different levels. It depends on whether you're a student of physics or an ordinary person who doesn't know anything or not. If you're somebody who doesn't know anything at all about it, all I can say is that there's a magnetic force that makes them repel, and that you're feeling that force. And you say, but that's very strange, because I don't feel kind of force like that in other circumstances. When you turn them the other way, they attract. There's a very analogous force, electrical force, which is the same kind of a question. And you say, that's also very weird. But you're not at all disturbed by the fact that when you put your hand on the chair, it pushes you back. But we found out by looking at it that that's the same force, as a matter of fact. The electrical force, not magnetic exactly in that case, but it's the same electrical repulsions that are involved in keeping your finger away from the chair, because everything's made out of its electrical forces in microscopic details. There's other forces involved, but this is connected to electrical forces. It turns out that the magnetic and the electric force with which I wish to explain these things, this repulsion in the first place, is what ultimately is the deeper thing that we have to start, what we can start with, to explain many other things that looked like they were, everybody would just accept them. You know, you can't put your hand through the chair. That's taken for granted. But that you can't put your hand through the chair, when looked at more closely, why? That involves these same repulsive forces that appear in magnets. The situation you then have to explain is why in magnets it goes over a bigger distance than in ordinarily. And there it has to do with the fact that in iron, all the electrons are spinning in the same direction. They all get lined up, and they magnify the effect of the force until it's large enough at a distance that you can feel it. But it's a force which is present all the time and very common, and is in a basic force of almost, I mean, I can go a little further back if I were more technical, but at an early level, I just have to tell you that's going to be one of the things you'll just have to take as an element in the world the existence of magnetic repulsion or electrical attraction, magnetic attraction. I can't explain that attraction in terms of anything else that's familiar to you. For example, if we say the magnets attract like as if they were connected by rubber bands, I would be cheating you. Because they're not connected by rubber bands, I shouldn't be in trouble. You'd soon ask me about the nature of the bands. And secondly, if you were curious enough, you'd ask me why rubber bands tend to pull back together again, and I would end up explaining that in terms of electrical forces, which are the very things that I'm trying to use the rubber bands to explain. So I have cheated very badly, you see. So I'm not going to be able to give you an answer to why magnets attract each other, except to tell you that they do. And to tell you that that's one of the elements in the world of the different kinds of forces. There are electrical forces, magnetic forces, gravitational forces, and others. And those are some of the parts. If you were a student, you'd go further. I could go further. I could tell you that the magnetic forces are related to the electrical forces very intimately. That our relationship between the gravity forces and electrical forces remains unknown, and so on. But I really can't do a good job, any job, of explaining magnetic force in terms of something else that you're more familiar with, because I don't understand it in terms of anything else that you're more familiar with.
Okay, that was Richard Fenneman there giving an interviewer a difficult time, shall we say, for asking what would appear to be quite a straightforward question. And that's really what I'm trying to get to here, is that it has been the querying of nature and the experimental application of the theories of the querying of nature. Essentially every theory, every scientific discovery is based on something known as an axiom. This is an initial premise. So you start with an initial premise, then you create an initial theory, a thesis. You then construct experiments to examine the truth or the failure of that thesis, and then should the experiment, the thesis and the axiom all agree, then you can begin to consider something as a theory, and ultimately, if it's proved repeatedly, then they usually go on to be considered as laws. A law is something that can be applied ubiquitously regardless of the circumstance. Right, we're going to move on to the fabulous Walter Lewin now. You know, he's one of my favourites, ex-MIT, now retired professor of physics. This is another one taken from his first year degree course. So this will be a degree course lecture to a class full of physics students, and this is his introduction to why quantum mechanics.
All physics of the 19th century and earlier is called classical physics. Examples are Newtonian mechanics, which we dealt with this whole term, and electricity and magnetism, which you will encounter the next term. In the early part of this century, when we learned about the composition of atoms, it became clear that classical physics did not work on the very small scale of the atoms. The size of an atom is only 10 to the minus 10 meters. If you take 250 million of them and you line them up, that's only 1 inch. In 1911, the English physicist Rutherford demonstrated that almost all the mass of an atom is concentrated in an extreme small volume at the center of the atom. We call that the nucleus. It's positively charged. And there are electrons, which are negatively charged, which are in orbits around the nucleus. And the typical distances from the nucleus to the electrons is about 100,000 times larger than the size of the nucleus itself. As early as 1920, Rutherford named the proton, and Chadwick discovered the neutron in 1932, for which he received the Nobel Prize. Now let us imagine that this lecture hall is an atom. And the size of an atom is defined by the orbits, the outer orbits of the electrons. If I scale it properly now in this ratio 100,000 to 1, then the size of the nucleus would be even smaller than a grain of sand. And it just so happened that yesterday I went to Plum Island, I walked for 3 hours on the beach, and I ended up with some sand in my pocket. And so I will donate to you 1 proton. Make sure you hold on to it. Ooh, that is 2 protons. That's too generous. So keep it there. This is 1 proton. Just think about what an atom is. An atom is all vacuum. You and I are all vacuum. You think of yourself of being something, but we are nothing. You can ask yourself the question, if you're all vacuum, why is it then that I can move my hand, not through the other hand, like a ghost can walk through a wall? That's not so easy to answer. And in fact, you cannot answer it with classical physics, and I will not return to that today. But you are all vacuum. According to Maxwell's equations, Maxwell's law of electricity and magnetism, an electron, because of the attractive force of the proton, would spiral into the proton in a minute fraction of a second. And so atoms could not exist. Now we know that's not true. We know that atoms do exist. And so that created a problem for physics. And it was the Danish physicist Niels Bohr who in 1913 postulated that electrons move around the nucleus in well-defined energy levels, which are distinctly separated from each other, and that the spiraling in of the electrons into the nucleus does not occur for the reason that an electron cannot exist in between these
allowed energy levels.
It can jump from one
energy level
to another, but it cannot exist in between. Now, Bohr's suggestion was earth-shaking, because it would also imply that a planet that goes around the sun cannot orbit the sun just at any distance. You couldn't move it just a trifle in or a trifle farther out. It would also require discrete energy levels. It would also mean that if you had a tennis ball and you would bounce the tennis ball up and down, that the tennis ball could not reach just any level above the ground, but it would only be discrete levels. And that is very much against our intuition. We'd like to think that when you bounce a tennis ball, that it can reach any level that you want to. You give it just a little bit more energy, and it will go a little higher. That, according to quantum mechanics, would not be possible. Now, all this seems rather bizarre, as it goes against our daily experiences. But before we dismiss the idea of quantization, you see the quantization comes in when you talk about discrete energy levels, you have to realize that the differences in the allowed heights of the tennis ball and the differences between the allowed orbits of the planets around the sun would be so infinitesimally small that we may never be able to measure it. In other words, quantum mechanics really plays no role in our microscopic world. Now, atoms are very, very small compared to tennis balls, and the quantization effects are much larger in the submicroscopic world of electrons and atoms than in our familiar world of baseballs, pots and pans, and planets. So before we continue, I would like to repeat to you one of the cornerstones of quantum mechanics. And it says that the electrons in atoms can only exist at well-defined energy levels, and they cannot exist in between. Now, when I heat a substance, the electrons in the atoms
can jump from low energy states to high energy states.
And when they do so, they can leave a hole, an opening, an empty
energy state.
But later on, they can fall back to fill that opening. They can occupy that
energy state
again. And when I keep heating this substance, there is some kind of a musical chair game going on. The electrons will go to
higher energy levels.
They may spend there some time, and then they may fall to
low energy levels.
You see here a vase, a very precious vase. And when I pick up this vase, I have to do work. I bring it further away from the center of the Earth. Now, is that energy lost? No. I could drop the vase, and it would pick up kinetic energy. I will get that energy back. Gravitational potential energy will be converted to kinetic energy. It will crash to pieces and it will generate some heat. In fact, the breaking itself of this vase would take some energy. In a similar way, the energy that you put into electrons when you bring them to
higher energy levels
is retrieved when the electrons fall back. So there is a parallel, dropping this vase and getting the work back that I put in. That wouldn't be a nice thing to do to this 500-year-old vase, but as far as I'm concerned, perfectly reasonable to do it with Ohanian. So we can let that go, and the energy will come out in the form of heat and also in the form of perhaps some noise. When electrons fall from
higher energy states to low energy states,
it's not kinetic energy that is released, but it comes out often in the form of light, electromagnetic radiation. Light has energy. Einstein formulated that a light photon, the energy of a light photon, is h times the frequency, and h is Planck's constant, named after Max Planck, and h is about 6.6 times 10 to the minus 34 joule seconds. Now we've also seen in 801 that lambda, the wavelength of light, equals the speed of light divided by the frequency. And so if I eliminate the frequency, I also can write that the energy of a light photon equals hc divided by lambda. And so you see, the more energy there is available, the smaller the wavelength. And the less energy there is available, the longer the wavelength. And so if the jump
from a high energy state to a lower energy state
is very high, then the wavelengths will be shorter than when the jump is relatively small. I can make you some kind of an energy diagram of these jumps. And these are energy levels, so energy goes in this direction.
This would be the lowest possible energy state.
So these would be allowed energy levels, allowed orbits. And if this electron had jumped all the way here, then it could fall back at a later moment in time, and the energy could be so much that you couldn't even see the light. It could be ultraviolet. And this jump may still be ultraviolet. But now this jump, which is a little less energy, that may be in the blue part of our spectrum. So we may see this as blue light. And this one, which is a little less than this energy, this jump may generate green light. And the jump from here to here, which is even less, may generate red light. And the jump from here to here, which is even less, may again be invisible. So this may be infrared. And so as the electrons fall
from a high energy state to a lower energy state,
you expect very discrete energies to come out, very discrete wavelengths. And these wavelengths that you would see correspond then to these allowed transitions between these energy levels. So if we could look at that light and sort it out by color, we would in a way see these energy levels. Now, you have in your little envelope a piece of plastic, which we call the grating, and the grating has the ability to decompose the light in colors, which we call a spectrum, and we're going to shortly use that grating to look at light from helium and light from neon. But before we do that, I'd like to hand out as a souvenir to a few people, randomly picked, something that they can also use. It's not as good as your grating, though, but it is also nice. You will see a more spectacular result, but not as clean. It's not as clean. All right. One for you, one for you, one for you, and one for you. And you want one, I can tell that, and you want one. And here. Two for you. For you. Oh, no, this side hasn't had anything. I got to walk all the way over now. So this is really for children's parties, which I'm handing out, whereas, oh, George Coster, you want one, of course. Professor Coster wants one. I couldn't bypass him. You want one? Okay, and you want one. So, by all means, use your grading, but then at the very end, you can always use this, these little spectacles, which don't work nearly as well, but this kind of thing. I'm going to light here this bulb, this light, which has helium in it. And what you're going to see with your grading, if you hold your grading properly, you may have to rotate it 90 degrees. You will see how that works when you try it. You're going to see very, very sharp, narrow lines at various colors. I want you to realize that the reason why you see very sharp, narrow lines is only because my light source, a very sharp, narrow line. If you use it on something that is not a very sharp, narrow line, then you're not going to see through that grading very sharp, narrow lines. So don't confuse the lines that are on the grading with the line source that I have here. Now when you look through your grading very shortly, you will see on both sides the wonderful lines. It's a mirror image, and we will discuss it in a little bit more detail. But before you look through your grading, I first want you to simply look at it without the grading. Because then it is even more spectacular when you lose the grading, because you have no clue when you don't use the grading what kind of colors are hidden there. And the colors that you're going to see are these electron levels. So I'm going to make it dark. And I will turn this on. And this one, I believe, is helium. I have a grading here. So you have to rotate it so that you see vertical lines on either side. You may have to rotate it 90 degrees, no more. And if you look closely, for instance, look on the right side of the light, you will see a distinct blue line, a few blue lines, green, very nice bright yellow one, and you see red. And if you go further to the right, you see a repeat. It's a little fainter, but you see a repeat of that. That's not important right now. I just want you to see that this light, which you have no idea that it comes out in very discrete wavelengths, very discrete frequencies, and they correspond to these jumps from allowed energy levels to other allowed energy levels, but there's nothing in between. And when you look on the left side, you'll see a mirror image of what you see on the right side. Now helium has only 2 electrons. And now I'm going to put in a neon bulb, and that makes it richer for reasons that neon has 10 electrons. So you have many more allowed energy levels, so many more ways that the electrons can play musical chair. A lot of lines in the red. I'm not blocking you, I hope. A lot of lines in the red, and some beautiful lines in the yellow. I see some in the green. I don't see much in the blue. Yeah, a little bit in the blue. But the key thing is, I want you to see that these lines are discrete. It is not just any wavelengths that can be generated. It's only the allowed energy levels, the musical game, when the electrons jump from one orbit to another. And that gives you this unique discrete spectrum.
Okay, so that was the first part of Walter Lewin's introduction to quantum mechanics. What he was suggesting there is that the witness spectral lines that you'll see through a particular type of lens, when viewed through very specific frequencies of light being generated by very well-known elements, that these are indicative of, well, now let's discuss it. The meaning of the word quantum is essentially in reference to these electron rings, that the electron can jump from ring to ring in what are known as quantum jumps or quantum steps, and that these steps are always whole steps, although the values are subject to the values of the measurement system that you're using. If you consider sort of one electron ring and another electron ring and another electron ring, that there's no chance of an electron arriving at ring 2.5 or ring 1 3/4. So that's the quantum of quantum mechanics. We're going to go a little bit deeper now. We have the wave-particle duality, which is the initial problem of Newtonian physics that created quantum mechanics in the first place. So it's really the first place that we have to now examine, now that we've established the whys of, or the whens, I suppose, the whats of quantum mechanics. So here we go, wave-particle duality.
Consider the innocent-seeming idea that even if none of us were there to see it, the world would still exist. Most of us don't believe that when we close our eyes, everything around us dematerializes, only to come back into existence instantaneously when we open them. Assumptions like this are very ingrained in our minds, and yet in quantum theory, many of our basic assumptions are false or seriously up for debate. So what is quantum mechanics? It's an attempt to explain a lot of strange phenomena that are often most noticeable when we look at particles smaller than atoms. But make no mistake, quantum mechanics isn't just the physics of small things. It's a complete overhaul of Newtonian mechanics, the explanation for why chemistry even happens, and just in general a huge rethink of how the world works. Our adventure into quantum mechanics starts off with the question, what is stuff? How does it act? We're all pretty familiar with how things act in our daily lives, so this question seems a bit trivial. But people discovered there was another side to stuff that becomes more obvious when you look at very small objects. They started to say strange things like, stuff acts like particles, but also like waves. We'll see how quantum mechanics solves that confusion by telling us stuff is even weirder than that. Firstly, what is a wave and what is a particle? And what are the telltale signs that you're dealing with one or the other? Particles are pretty familiar to us. One thing about them is that they're localized to one area, whereas waves are very spread out and in more than one place at once. There's another way that waves are very different from particles, and that's how they interact with each other. Particles do this, whereas waves can do crazy things like this. This phenomena is called superposition or interference. Basically, when two waves meet, they can either reinforce each other, or cancel each other out, or do a bit of both. You can use these two properties of waves to design a pretty clever experiment that tests whether you're dealing with waves or particles. It's called the double-slit experiment, and seriously, you're going to want to remember this one because, in my opinion, it's the most important experiment in quantum mechanics and we'll come back to it so many times. First, we'll talk about the experiment when it's done with small particles. You need a gun that will shoot the particles here. Then put up a board that will detect where the particles land. In between, you set up another board, but one with two slits in it that the particles can get through. What happens when you shoot the particles? Most won't get through, but those that do will mostly end up in two big clusters behind the holes. The situation with waves is very different. We'll have the same setup now, except we'll create the waves at this end, and at the other end, we'll measure where the waves hit with the most intensity. First, we'll cover up one hole and see what happens. The wave goes through the hole and then starts to make these semicircular wavefronts. Therefore, the wave hits most intensely right behind the open slit. So you might expect that when both holes are open, that the pattern will look something like this. But it doesn't at all. When both slits are open, the wave splits up and then interferes with itself. When two peaks or two troughs meet, they make a bigger peak or trough. Where a trough and a peak meet, they cancel each other out. Imagine that these are water waves and you're in the water. If you're in these waters, you're getting bobbed up and down a lot. On the other hand, these waters are pretty calm. So at the wall, you can expect the waves to hit most intensely around these areas and least in these. So you'll get a pattern like this for intensity. Most things that we're familiar with seem to act like particles, so people expected that even when we're dealing with things so small that we couldn't see them with our eyes, they'd be particle-like. Let's put that to the test using the double-slit experiment on something extremely small, say an electron. We won't be able to see the electron as it goes through, but what we'll do is put a special screen in on this side that lights up whenever the electron hits it. We're going to use an electron gun that only fires one electron through at a time. Here goes. Well, that looks like particles to me, because a wave would be spread out across the whole screen, not arriving in these localized dots. But wait, look at the pattern forming on the screen. That's not what we'd expect of particles at all. In fact, I'll show you that this result seems impossible. First, let's see what happens when we cover up one slit. We get one big splodge of points behind the open slit. Okay, but what we just found was that the electrons are like particles in that they're in one spot and not spread out, so each electron must go through just one slit. But we already know that electrons going through this one slit must make a pattern like this, and similarly for electrons going through the other slit, so we should expect this, which is not what we're getting at all. This result seems to defy logic, and that is a big problem for physicists. You see, if the universe is inconsistent with itself, there would be no point in trying to make sense of it. It wouldn't work, and physicists would be out of the job. Luckily for us, a few smart people came up with a cunning solution. The solution is called quantum mechanics, and if it's troubling, then please just remember, we were desperate. You see, our previous reasoning implicitly assumed many things that we usually hold to be true, but if we can let a couple of these go, then we can come up with a solution. Our first assumption was that because the electron looks like a particle when it's observed, that means it's a particle while we're not observing it. This is the kind of assumption that is really important in science. We like to think that our experiments are simply unveiling the reality that was already there, rather than changing it completely. Quantum mechanics lets that comforting idea go. Instead, while we're not looking, quantum mechanics doesn't say anything about the actual electron itself. Instead, it talks about something called the electron's wave function. The wave function is this wave that exists at all times, even when the existence of the electron itself becomes questionable. It's a wave similar to a water wave. Therefore, in the double slit situation, it interferes with itself, so the intensity profile of the wave looks like this, just like with water waves. Okay, great, we've got this wave, but what on earth has it got to do with our electron? This is where we need to let go of our second assumption. Basically, ever since Newton, physicists have believed that there isn't random chance in how our universe acts. If you think back to our experiments with regular particles, we said that they didn't all land in the same spot. However, according to Newton's laws, this is just because they must have been going in slightly different directions and speeds at the start. If we could get them all exactly the same, they'd fall in exactly the same spot. In quantum mechanics, though, the opposite is true. Even if it were possible to get the electron gun to shoot in the exact same way each time, the electrons wouldn't all land in the same spot. There is an element of chance involved, and there is absolutely no way to predict where a particular electron is going to go. That's like saying, when I let an apple go, 2/3 of the time it'll fall down, and 1/3 of the time it'll fall up, for no reason, and there's no possible way to predict which way the apple will fall next time you drop it. However, quantum mechanics doesn't say that where our electron will turn up is completely random, because then our pattern would look like this. On the other hand, what we get for the double slit experiment is this, and for the single slit one, this. We can see the electrons seem more likely to turn up in some spots, but how do we figure out where? Re-enter the wave function. Remember, the intensity profiles for the wave function in each case is like this and this. As you can probably guess now, the electrons are most likely to turn up where the intensity of the wave function is big. If you want more details on how to exactly calculate this, then let me know in the comments and I might make a video about it. Okay, so let me recap. When we're not looking, the electron itself may or may not exist, but in its place is some sort of wave. Quantum mechanics says that while you're not experimenting on it, the electron doesn't have a position. Even its wave function is spread out. But when we attempt to measure the position of the electron, the universe realizes it needs to produce an electron, so it picks where the electron will turn up semi-randomly based on its wave function. Yeah, I know. Well, I'll leave you with that for now, and next week I'll try and expose you to more of this quantum mechanics thing, but I'm sorry, it really only gets weirder. I hope you have a bunch of questions. Please ask them all, and I'll answer them if I think I know the answer. See you next time.
And we're back. As usual, just fabulously impressed with the level of knowledge already existing in the chat. It seems that I'm singing to the choir, as they say. So I'm going to move ahead with some pace, so I'm not keeping you up after 2 a.m. Right, we're going to have a bit more Waterlooing next. This is now Waterlooing discussing Heisenberg's uncertainty principle. Trying to keep as much of the sort of quantum math out of the audio as much as possible. There are some references to it. You will hear Walter scribbling a few algorithms on the blackboard. I think to some degree that you need to leave some of this in. This is where the Omniversity separates from mainstream media. I am not playing to an audience where I'm assuming that the intellectual age is a reading age of 12. Okay, I respect you guys a lot more than that, and I anticipate that your reading age is much greater than 12 and that you can cope with a lot of this audio. Certainly the feedback that I'm getting about the Omniversity shows are incredibly rewarding. So I'm going to power ahead. This show is just going to get more complex. So if I've already lost you, I don't know, perhaps go and watch a rerun of last week's Coronation Street or something. You know, you might be missing out on something. Anyway, Heisenberg's uncertainty principle, deeper into quantum mechanics now.
Now, one of the startling consequences is that protons and electrons, which everyone at that time considered particles, can then also be considered as being waves. And in 1926, the Austrian physicist Schrödinger drove the nail in the coffin with his famous equation, Schrödinger's equation it's called now, which is the ground pillar of quantum mechanics, and it unifies the wave and the particle character of matter. Returning to my baseball, take a mass of the baseball of, say, 0.5 kilogram, and give it a speed of 100 miles per hour. Calculate the wavelength that you would find, according to quantum mechanics. That wavelength is so absurdly small, so it is completely meaningless. So quantum mechanics plays no role in our microscopic world of pots and pans and baseballs. But now take an electron. You take the mass of the electron, 10 to the minus 30 kilograms, and you give the electron a speed of, say, 1,000 meters per second. Now you get a wavelength which is comparable to the wavelength of visible light, red light. And now it's something that becomes very meaningful, something that can be measured. Now you may argue, gee, what difference does it make? Who cares whether something is a wave or whether something is a particle? Well, it makes a huge difference. Because waves have crests and they have valleys. And so if you take two sources of waves, either water waves, two sources, tapping up and down on the water, or you can take two sound sources, then there are certain locations on the surface of the water where the crest of one wave arrives at the same time as the valley of the other. And so they cancel each other out. There is nothing, there's no motion of the water. We call that destructive interference. Of course, there are other places where there is constructive interference, where they support each other. Now, if particles can do that too, that is very hard to imagine. How can one particle with another particle interfere and vanish, that the two particles no longer exist? So if indeed particles are waves, you should be able to demonstrate that by having the interference pattern of two particles like the water waves and make at certain locations in space those particles disappear, which turned out to be possible. But that's a very non-intuitive idea. So we think of it too classically when we say, well, two particles cannot disappear. But in quantum mechanics, you can think in waves if you want to, and then you have no problems with the interference pattern and the destructive interference at certain locations. Now, there are other remarkable consequences of quantum mechanics in classical mechanics. If you and I are clever enough You think that we should be able to determine the position of an object to any accuracy that we require, and at the same time determine also its momentum at any accuracy that we require. Just a matter of how clever we are. Simultaneously, the object is right there, and that is its mass, and that is its speed. However, the German physicist Heisenberg realized in 1927 that a consequence of quantum mechanics is that this is not possible. Strange as it may sound to you, Heisenberg stated that the position and the momentum of an object cannot be measured very accurately at the same time. And I will read to you Heisenberg's uncertainty principle, the way we know it. It says the very concept of exact position of an object and its exact momentum together have no meaning in nature. It is a profound non-classical idea, and it is hard for any one of us, you and me included, to comprehend. But it is consistent with all experiments that we can do to date. I want to repeat it, because it's going to be important of what follows. The very concept of exact position of an object and its exact momentum together have no meaning in nature. What does it mean? First, let me write down Heisenberg's uncertainty principle. Delta P, which is the uncertainty in the momentum, multiplied by delta x, which is an uncertainty in the position of that particle, is larger or approximately equal to Planck's constant divided by 2 pi, for which in physics we call that h bar, and h bar is approximately 10 to the minus 34 joule seconds. You see h is 6.6 times 10 to the minus 34. If you divide that by 2 pi, you get about 10 to the minus 34. What does this mean now? What it means that if the position is known to an accuracy delta x, and we'll give you some examples, that the momentum is ill-determined, is not determined to the amount delta p larger or equal than h bar divided by delta x. That's what it means. And I'll give you an example which I've chosen from a book of George Gamow. Gamow wrote a book which he called Mr. Tompkins in Wonderland. It's about dreams. Mr. Tompkins wants to understand the quantum world. And there is a professor, you will see a picture of the professor, who takes him in his dreams along the various remarkable, non-intuitive effects of quantum mechanics. And in one of these dreams, the professor suggests that we make h bar 1. And the professor takes a triangle on the pool table, and he puts the triangle over one billiard ball. So the billiard ball is constrained in its position, and that delta x is roughly, say, 30 centimeters, 0.3 meters. That means that the momentum is not determined to an approximate value of 1 divided by 0.3 is about 3 kilogram meters per second. Now, if we give the billiard ball a mass of 1 kilogram, then delta P is m delta V. And so if m is 1 kilogram, then the speed of that billiard ball is undetermined, according to Heisenberg's uncertainty principle, by at least approximately 3 meters per second. 3 meters per second, that means 7 miles per hour. And so that billiard ball will go around like crazy in that triangle. And that's exactly what happens in the dream. And I will show you here a picture from that book. Mr. Tompkins is always in pajamas, just to remind you that it is a dream. And needless to say, the professor is a very old man and has a very nice beard. It adds to the prestige. And I will read you from this book. I will read you a very short paragraph that deals with this. So the professor says, look here, I'm going to put definite limits on the position of this ball by putting it inside a wooden triangle. As soon as the ball was placed, in the enclosure of the hole inside of the triangle became filled up with glittering of ivory. You see, said the professor, I defined the position of the ball to the extent of the dimensions of the triangle. This results in considerable uncertainty in the velocity, and the ball is moving rapidly inside the boundary. Can't you stop it? Asked Mr. Tompkins. No. It is physically impossible. Any body in an enclosed space possesses a certain motion. We physicists call it zero-point motion, such as, for example, the motion of electrons in any atom. So here you see quantum mechanics at work when h bar is 1. This is a very non-classical idea, because you and I would think, and we've always dealt with that in 801, that you can take an object and place it at location A, and we say at time t0, it is at A, and it has no speed, and we know the mass. So we know both the momentum and the position to an infinite accuracy. But according to quantum mechanics, that's not possible. So let's now return to the real world, where h bar is not 1, but where h bar is 10 to the minus 34. And let's now put a billiard ball inside this triangle. Now, delta x is the same, but since h bar is 10 to the minus 34, delta p is, of course, 10 to the 34 times smaller, and so the velocity is 10 to the 34 times smaller. This undeterminedness, degree to which the velocity is now undetermined, is so ridiculously small, it is 3 times 10 to the minus 34 meters per second, that if you allowed that ball to move with that speed, in 1 billion years, it would move only 1/100th of a diameter of a proton, so it's meaningless again. And so again you see that quantum mechanics plays no role in our daily microscopic world of baseballs and basketballs and billiards and pots and pans. And therefore it is completely okay for us to say, I have a billiard ball, which is at point A, and its mass is 1 kilogram, and it has no speed. That is completely kosher, completely acceptable, and quantum mechanics has no problems with that. Let's now turn to an atom. Take a hydrogen atom. The diameter of a hydrogen atom is about 10 to the minus 10 meters. So the electron is confined to a delta x of about 10 to the minus 10 meters. That means the momentum of that electron becomes undetermined, according to Heisenberg's uncertainty principle, to about 10 to the minus 34 divided by 10 to the minus 10 is about 10 to the minus 24 kilogram meters per second. What is the mass of an electron? That's about 10 to the minus 30 kilograms. So this, delta P, is also m delta V. So it means that delta V, that means the velocity of the electron, is undetermined, according to Heisenberg's principle, by an amount which is at least 10 to the minus 24, which is this delta P, divided by the mass of the electron, which is 10 to the minus 30. And that is about 10 to the 6 meters per second. That is 1/3% of the speed of light. So the electron is moving only because of the fact that it is confined. That's what quantum mechanics is all about. The electron's motion is dictated exclusively by quantum mechanics.
The glorious Water Lewin there, completely distracting me, and Dell in the chat as well, discussing quantum mechanics as we go. Cracking quantum mechanic jokes. I think that's certainly one for the books. Right, what have we got up next? We're moving into the EPR paradox. This is now where Einstein first enters the fray. And the EPR paradox is the Einstein, can't remember who the P is, but the R is Rosenberg. And this is basically the argument that they had with the whole concept of entangled particles being able to interact at greater than light speed, because that essentially defied Einsteinian relativistic mechanics. Anyway, here we go with EPR paradox, entanglement and the quantum model.
So far, I've been telling you about the theory of quantum mechanics and how it tries to answer questions about reality. Today, we're going to do something a little different and actually question quantum mechanics itself. I've been looking forward to this. In this video, we're going to look at a paradox Einstein helped create to disprove quantum mechanics. To understand it, we need to know about an essential ingredient in quantum theory, entanglement. Entanglement isn't actually something limited to quantum. Consider this example. You have two objects, one red and one white. You put them into boxes and shuffle them around. Now, if you open one of the boxes and see the object is red, then you know without having to check that the other box has the white object in it. So we say that these two objects are entangled, which means that knowing something about one causes you to know something about the other, without ever having to look. However, quantum entanglement is much more interesting than this garden variety. Of course, the culprit, as it always is in quantum mechanics, is superposition. Let's go back to our example. While the boxes are closed, we don't know which state the object in each box is in, red or white. If it were truly impossible to know, which isn't actually the case in everyday life, but let's say it is this time, then quantum mechanics tells us that each object must be both red and white at the same time. But it's even weirder than that. There are two possibilities. Either A is red and B is white, or the other way around. But superposition tells us that all possible things happen at once. So the state of the two objects is both A is red, B is white, and A is white, B is red. Now this is a bizarre superposition. What happens if Alice checks object A? She collapses the state of object A, which is weird but as usual. But she also collapses the state of B, which she didn't even touch. I'm sure at this point that a lot of you are skeptical. Why should we accept the quantum picture when it's obvious that the classical version has the same results by a far less convoluted method? Couldn't it be the case that objects aren't actually in superpositions at all? This is a very good concern, and one we'll be taking seriously. We're going to try and build a test. First, let's notice something. In quantum mechanics, these particles are not independent of each other in a deep sense. You could argue that the classical particles aren't either, but here's the difference. In the classical case, measuring one of the particles, say finding out that it's red, doesn't actually turn the other one white. In fact, it does nothing to the other one. The objects already had a color all along. On the other hand, according to quantum mechanics, the objects have to affect each other. Otherwise, each object is in a superposition of red and white, and Alice could measure hers and find it's white, but this doesn't do anything to B's superposition, so Bob could measure B and find it's white as well. But this can never happen. The EPR paradox is a brilliant and simple argument that exploits this difference between the classical case and the quantum one. The authors wanted to show that, even though it seems like both the classical and quantum explanation can explain this experiment, the quantum one actually can't. It's a proof by contradiction, which means that you assume something, in this case that quantum mechanics is true, and then show that that would lead to something impossible happening. Therefore, the assumption must have been false all along. Actually, we don't need to assume all of quantum mechanics is true, just one little fact. We need to assume that if we have an entangled pair, A and B, then measuring A really does affect B. We saw that quantum has this quality, while classical mechanics does not. But we don't need to worry about superposition, etc. for this argument, just this one little fact alone. Okay, so now, say that our boxes get shipped to the other sides of the universe, to Alice and Bob. Alice opens hers a split second before Bob opens his. Alice finds her object is red, so Bob must find that his is white. But let's think about what must happen in that split second between when Alice unboxes her object and Bob does the same. A must tell B that it's been measured and what result it decided to be, or else B won't know what to do. But that message has to go an awful long way in a very short time. In fact, even light couldn't go that fast. This is a big problem. If you've heard of Einstein's theory of relativity, you might know that the fact that nothing can go faster than the speed of light is the foundation of that whole theory. Therefore, accepting our assumption that A and B can really influence each other is equivalent to pulling the rug from underneath relativity. To Einstein, this was impossible, so he concluded that the assumption must be wrong. Let's not be so certain. What are the possibilities? The first possibility is that the assumption really is wrong. Well, that definitely rules out quantum mechanics, but it's actually even stronger than that. It says that no theory where measuring one object changes the other object can ever be true. But then how can we explain that A and B always have opposite colours? We must do it the way classical mechanics did, i.e. none of the quantum weirdness, no superposition, no randomness, no uncertainty principle. So these are the two possibilities. Either we must believe that nothing can go faster than the speed of light and accept that quantum mechanics is completely false, or we accept quantum mechanics, but we discard the theory of relativity. We can't have both.
Okay, that's the EPR paradox, one of many of the quantum mechanics induced paradoxes, shall we say. Paradoxes are often just theories that contradict each other, but in the case of the EPR paradox, we're now beginning to get various experimental evidence that's partially contradictory. Right, I'm going to move on rapidly. Some fairly dismissive comments about Schrödinger in the chat earlier. Well, we're going to move on to Schrödinger now, but this is the sort of powerful experimental part of Schrödinger's theories, and this is the discussion of, or a description of Schrödinger's work on the probabilistic nature of the position of the electron on the hydrogen atom, which is a key part to motivating the quantum revolution.
Quantum mechanics and the shape of atoms as discovered by Schrödinger. We all know about quantum mechanics, which is of course the physics theory that describes atoms and elementary particles, how they move around like slushy little waves, and interestingly, it predicts what they look like, what shape they have. It was invented in the first couple of decades of the 20th century by a lot of people all working together. Amongst them were Planck, Heisenberg, Bohr, Davison, de Broglie, Einstein, and of course Schrödinger. These guys already knew a lot about atoms from the scientists who came before them. For instance, they knew that there are about 100 different atoms in nature, and that these atoms join in larger structures such as molecules, metal lattices, and salt lattices to make everything we see around us. But what they didn't know, what exactly was going on the inside of the atom, what it was made of, what shape it has. So they were doing experiments on that. And pretty soon they found out that atoms themselves are composed of smaller particles. They found the proton and the electron, and they were featherizing the neutron. And with the protons and neutrons, they almost immediately knew what the deal was. They realized that they were clumped in a very tiny core at the center of the atom. And that core was really small. A typical atom is about 300 picometers across, whereas that core is typically 0.01 picometers. So this leaves this big open space in an atom, and they realized that this open space was going to be the domain of the electron. But what they didn't know was exactly how the electrons are filling this space, if they are spinning around or orbiting or what. So they made an initial sketch. They called it the planetary model of the atom, basically the core at the center and the electrons spinning around in big orbits. It was their first idea of what an atom looks like. It proved to be incorrect, but it was a fine enough starting point. It made some very nice predictions, and it allowed them to start doing experiments, and they did. One man who was looking at these experiments was a Frenchman called de Broglie, and he was noticing something very interesting. He found that when electrons were forced to interact with matter, either through some physical process or by hitting a detector, that the electrons presented themselves as particles, as hard little balls of matter. Kind of what you expect them to do. But when the electrons were allowed to move on their own, either by being shot through a crystal or allowed to wander through a vacuum, they always propagated as if they were waves. It was almost as if when you stop messing around with the electron, it would suddenly fall apart into some sort of wave function, some sort of probability wave that sloshed around all of space and predicted where the electron was likely next to be found. This was the first time they encountered particle-wave duality in matter, and it spelled disaster for their planetary model. Because this model really assumed that the electron stays a particle during the entire orbit and doesn't fall apart into a wave halfway through. So, they needed a new model, but they realized that this model couldn't come from classical mechanics, because classical mechanics makes the same assumption that particles stay particles. In fact, they would need entire new mechanics, some new theory that included the wave-like nature of particles. And this is when Schrödinger entered the picture. He had looked at the experiments as well, and he found one common theme running through all of them. In his insight, he saw one law of nature, one equation that seemed to hold no matter what you did. He called it the wave equation. Nowadays, we simply know it as the Schrödinger equation because it was the rock-solid core onto which all of quantum mechanics was built. Schrödinger realized that with this equation he was now in a very interesting position. What he could do is take an atom, any atom, take its properties, stuff like its mass and its charge, all those numbers, put that in that equation, do the math on it, and what he would end up with would be a series of pictures that showed what that atom looks like. He went on and did it for hydrogen, which is the easiest atom, it's just one proton, one electron. And that one proved to be crucial into unlocking the shapes of all the other atoms. And when he had worked his way through the math, these are the pictures he found. Ladies and gentlemen, the shapes of hydrogen. So this then is how an electron fills the empty space in an atom, not by spinning around, but instead with its blobby shaped wave function, which we call the orbital. What I've drawn here each time is just the same hydrogen atom with a proton at the center, and the electron has been allowed to go into a different orbital each time by giving it energy, for instance. And if you look at this one, these three blobs together form that one orbital. They house that one single electron. And this one makes a fine example. We can look a bit at its properties. What you can do in an experiment is take a hydrogen atom and prepare it in this orbital by giving it some energy, for instance. And if you leave it undisturbed, then the electron takes this shape. It becomes this wave function, this blobby shape. And if you then were to take a measurement of the electron, find out where it actually is, what would happen is this wave function suddenly collapses. It condenses into a single point, which we call the electron. If you then were to re-prepare your hydrogen atom in the same orbital, maybe give it some new energy, then you can do a new measurement, and you can find that electron in the same blob, or in any of the other blobs. And if you were to repeat this thousands of times, you would end up with a picture very much like this. Notice that there's a higher probability of encountering the electron at the center of a blob. There the probability wave function becomes more dense. But there's something interesting about these pictures, of course, something that is, well, staring us in the face. The fact that these blobs are not connected. There's an area in between where you cannot encounter the electron. So it kind of begs the question, how on earth is the electron traveling from one blob to another? Is it teleporting or what? This was one of the important questions that led to 40 years of heated debate that ended up with Einstein saying very angry things about dyes. But who cares? Schrödinger had made an important discovery. He had found the shapes of hydrogen. And using that as a basis, those that came after him were able to find the shapes of all the other atoms. They are very much based on hydrogen. They use the same orbitals. It's just that the higher atoms consist of more electrons, therefore they require more orbitals to house all of them. So you end up with a situation where the orbitals all get stacked on top of one another, overlapping but not mixing. They do, however, repel, because that's what electrons do, they repel one another. So the orbitals begin distorting each other according to some very complicated math. But these guys were also good at what they were doing. And, combined with Schrödinger's discovery, they had now made a link between physics and chemistry. A link which in fact led to an entire revolution in both of them. So with that, I would like to conclude by just saying, Mr. Schrödinger, thank you very much.
Cut a bit short there. Yes, the Schrödinger's probability equations leading to the fundamental modelling of the structure of the atom, and it's not at all spherical. Even the most basic of electron probability graphs that Schrödinger came up with was more or less just a donut around the nucleus, but they got a lot more exotic beyond there. And the key point there is that without these Schrödinger's models of the hydrogen atom and the discoveries that led to, the modern chemistry revolution and biochemistry revolution would simply not have been possible. So, again, moving on briskly so as not to keep us up too late. Got some even deeper into the sort of advanced parts of the quantum mechanics experiments, back to the wonderful Walter Lewin, and now we're going into the advanced double slit experiments. Again, basic double slit, but a more advanced description of it, and including some of the tortuous quantum mechanical maths. But again, no real need to pay any attention to that. I just left some of it in where it was salient to illustrate as to just how complex some of the algorithms behind this work is.
I'm going to show you an experiment in which I want to convey to you how non-intuitive Heisenberg's uncertainty principle is. I have here a laser beam, and this laser beam is going to be aimed through a narrow slit. I'll make a drawing. I'll turn this light off. And that slit, which is a vertical slit, can be made narrow and can be made wider. Here is this light beam, and here is this opening, this slit. It's only going to be confined in this direction, not in this direction. And so the light will come out here, and then on a screen, which is going to be that screen, the large distance, capital L, we're going to see that light spot due to the light beam going through the slit. And this separation, capital L. I start off with the slit all the way open. And so you're going to see this light spot like this. And then I'm going to make the slit narrower and narrower. And as I'm going to cut into the light beam, what you're going to see is exactly what you expect. You expect that this light disappears, and when I cut in further, you see exactly what you expect, that this light disappears. And so the light spot there on that screen will become narrower and narrower and narrower. But then there comes a point that Heisenberg says, careful now, because your delta x, your knowledge, the accuracy in this direction where the light goes through is now so high that now I'm going to introduce an uncertainty in the momentum of that light. The momentum of that light is now no longer determined to infinite accuracy. And what that means, if you start fooling around with the momentum of that light in the x direction, it no longer goes through straight, but it goes off at an angle. And I will make you a more quantitative calculation for that. So let's look at this slit from above. Here's the slit. And the slit has an opening delta x. And this delta x we're going to make smaller and smaller. And let us start with a delta x of about 1/10 of a millimeter, which is 10 to the minus 4 meters. I have light. I know the wavelengths of the light. And I know that lambda equals h divided by p, according to de Broglie. I know the wavelengths. I know h, and so I can calculate the momentum of that light. I have done that. Take my word for it. It is about 10 to the minus 27 kilogram meters per second. That's the momentum of the individual light photons. Think of them as particles, which you can do according to de Broglie. So now, I have a delta p. The degree to which the momentum is undetermined, according to Heisenberg, is going to be 10 to the minus 34 divided by delta x, which is 10 to the minus 4th. So that is 10 to the minus 30. Very small. But the momentum itself is 10 to the minus 27. So it's only 1 part in 1,000. So what will happen if the light comes through here, and I now make a classical argument. I say this is the momentum of the light as it comes straight in. When it has to be squeezed through this narrow opening, Heisenberg's uncertainty principle demands that it's going to be undetermined, the momentum in this direction, by roughly 10 to the minus 30 or more. Remember, it's always larger or equal. In other words, if I introduce, for instance, in this direction or in this direction, delta p, then I would expect that some of that light goes off in this direction. It is this change in momentum, this undeterminedness in momentum, that makes it go off in an angle. Only in the x direction. If I have the slit like this, don't expect this to happen in this direction, because the uncertainty in the y direction, that's not the problem. Delta y is not very small, it's delta x that is very small. So it's this direction that's going to give you trouble. It's only in this direction that you know precisely where that light goes through. This direction is not the issue. So this angle theta can now be calculated very roughly. Theta is obviously delta p divided by p. So theta is very roughly 10 to the minus 3 radians, which is a 15th of a degree. And if you have at a distance L, if this distance here is L, if you have here a screen, then the spot on this screen, if I call that x at location L, then x at location L is obviously theta times L. And if theta is 10 to the minus 3, and let's assume this is about 10 meters away from us, so L is about 10 meters, then you get 10 to the minus 2 meters. That is 1 centimeter. 1 centimeter in this direction, and 1 centimeter in that direction. 2 centimeters. But when I make the slit width 10 times smaller, if I make the slit width only 1/100th of a millimeter, then this becomes 10 centimeters. Because now I know delta x 10 times better, and so delta p is 10 times more uncertain. So now I expect to see here at least a smear of 20 centimeters and at least a smear of 20 centimeters there. So the absurdity is that a teeny-weeny little light source, which in the beginning you will see as a very small spot, when I make this slit narrower and narrower, indeed you will see that you will lose photons, and you will see this getting narrower and narrower, and then all of a sudden it begins to spread out, and it begins to spread out, and by the time I'm close to 1/10 of a millimeter, the light spot there will be yay big. Very non-intuitive. You make the slit smaller, and the photons spread out. And I want to show that to you now. I have to make it very dark. And I need my flashlight. Turn on the laser beam. Yeah. There you see it. The slit is now all the way open. Yeah, it's all the way open. And I'm going to close the slit now slowly. And if you look closely, you will see that let me also get my red laser, then I can point something out. You will see that the light will get squeezed in the horizontal direction. You can see already that the left side has a very sharp vertical cutoff and the right side also. It's getting narrower. It's getting narrower. Getting narrower, but I'm nowhere nearly a tenth of a millimeter yet. It's getting clearly narrower. You see it's getting narrower, it's getting narrower. Now if I look here, oh, I'm not yet at the tenth of a millimeter, but I'm getting there. Going slowly, squeezing it. I'm squeezing those photons. Those photons now are forced to go through an extremely narrow opening, and Heisenberg is very shortly going to jump in and says, you're going to pay a price for that. You know too well where those photons are in the x direction. The price you pay, that nature will now make the momentum undetermined in the x direction. And you see it now. You already begin to see that the center portion is widening. Even photons appear here. You see some dark lines, which I will not further discuss today, but notice that the light is spreading. Of course, when I squeeze this slit, when I make it narrower, it's obvious that I lose light, because the light that hits the side of the slits is not going through. So the light intensity will go down. That's just inevitable. I use fewer photons. But look at this. There are photons here, there are photons there. It's at least 10 centimeters, this portion. From here to here is at least 1 foot. I squeeze more. This is more than half a meter now. I squeeze more. This is about 1 meter already. Now, not only have you seen quantum mechanics at work in terms of electrons jumping between allowed energy levels, but you now have also seen one other very interesting consequence of quantum mechanics, which is Heisenberg's uncertainty principle. Now, the spreading of this light can very easily be explained without Heisenberg's uncertainty principle. In fact, it was known, even in the previous century, to a high degree of accuracy, why this happened, and the dark lines were very accurately explained. All I wanted to show is that this spreading of the light is entirely consistent with Heisenberg's uncertainty principle. And it better be, because it would not be possible, it would be inconceivable that you could do any experiment that would violate Heisenberg's uncertainty principle. And if this light that you would see on the screen there, if that light spot would get narrower and narrower and narrower and narrower all the time, as we would think classically, that would have been a violation of Heisenberg's uncertainty principle. And that is not possible. Now, there is no way in advance to predict which photons end up where. All you can do with quantum mechanics is to do the experiment with lots of photons, and then you will get a certain distribution, and the distribution will be exactly as you saw there. Quantum mechanics can never predict on an individual photon where it will end up. We saw that bright spot in the center. So if you did this experiment with 1 photon per day, 1 photon per day going through this slit, and you would have a photographic plate there, and you would keep it there for months, and you would develop it, you would see the same pattern that you see there. This photon arrives today. Here arrives one tomorrow. Here arrives one the day after tomorrow. Here one the day after that. 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 And slowly are you beginning to see that pattern that you saw. So don't think that this interference pattern that you saw is the result of 2 photons going through the slit simultaneously. Not at all. You can do it with 1 photon at the time, and you would see exactly the same thing. Now, this idea that you cannot in advance predict what a particular photon will do is a very non-classic idea, and it rubs us all the wrong way. Because our classical way of thinking is, and you are no different from my own feeling in this respect, that if you do an experiment 100 times in a controlled way, you should get 100 times exactly the same result. Not so, says quantum mechanics. All that quantum mechanics will tell you is what the probability is that something will happen. No guaranteed, but it is very good in predicting probabilities. Now, Einstein had great problems with this idea of not knowing precisely what would happen, and he had endless discussions with Bohr and others in which he tried to convince them that because you couldn't predict what happened, that something had to be wrong with quantum mechanics. And Einstein's famous words were, "God does not throw dice." This was it was his way of saying it is ridiculous that the outcome of a well-controlled experiment is uncertain. Now, almost 9 decades have gone by since the beginning of quantum mechanics, and we now know that God, if there is one, does throw dice. However, God is bound to the rules of quantum mechanics and cannot violate Heisenberg's uncertainty principle. The light could not go straight through without spreading when I made the slit as narrow as I did. So quantum mechanics is a bizarre world that we rarely experience in our daily lives because we are used to basketball, baseballs, tennis balls. But yet, it is the way the world ticks. And atoms and molecules can only exist because of quantum mechanics. That means you and I can only exist because of quantum mechanics. I hope that this will give you something to think about. But I warn you in advance, because if you start thinking about this, it will give you headaches, and it will give you sleepless nights. And it has given me countless sleepless nights in the past, and even today when I think about the consequences, the bizarre consequences of quantum mechanics, I still cannot comprehend it, I still cannot digest it, and I still have headaches and sleepless nights. But it may be necessary to go through these sleepless nights if you want to eventually evolve as an independent thinking scientist, and I hope that someday all of you will. Thank you.
Okay, so with that Waterlooing, I conclude my exploration of the experimental evidence behind quantum mechanics, and we're going to take a slight departure now into a dismantling of Einsteinian relativity. The fabulous Steve Carruthers does a lot of work exploring the more ridiculous claims of modern cosmology, and in this one specifically he homes in on general relativity, and this runs to 50 minutes. I don't know, that would leave us overrunning 2 a.m. I might question the chat to see as to whether people would rather I cut it short and move on to the next area, but essentially I'm now moving into the area of an exploration of the paradoxes at the fundaments of our modern physics, and to some degree exploring the things that need to be done about that situation. Anyway, here's the science thug Steve Carruthers taking general relativity out the back and giving it a good kick in.
Good afternoon, ladies and gentlemen. I'd like to thank the EU and Thunderbolts Project for inviting me here to speak to you today. Thank you for coming along and listening to what I have to say. Now, the title of my talk is General Relativity, a Case Study in Numerology. Now, I mean that both facetiously and literally, because I'm going to show you today, using mathematics and numbers, that general relativity and all its associated things such as black holes and big bangs are really nothing other than some kind of numerology. And to begin, I'd like to dedicate my talk today to these three late musicians: John Lord from the rock group Deep Purple, And these two men, Huey Thomason Jr. and Billy Jones, from the southern rock band, The Outlaws. Some of you, as old as me or older, will certainly remember them. The first thing I'd like to do is to begin by baking a cake. Now, what kind of a cake it is? It is a cosmological cake. The first thing is a bit of a recap before I go into mathematics of all of this, is things that I've spoken of in the past by comparing the characteristics of black hole universes to Big Bang universes and seeing simply the very simple underlying contradictions that make them impossible. Now, the first thing is black hole universes are spatially infinite. There are three types of Big Bang universes, one spatially finite and the other two are spatially infinite, depending on their K curvature values. The black hole universe is eternal. That means it's static. It doesn't depend on time. Whereas Big Bang universes are all finite in age. They're 13.8 billion. I believe that they've now raised it to 13.9 by tweaking a few knobs. Now, the black hole universe is, by definition, something that only contains one mass. Well, that doesn't really correspond to what we see in the sky. I see at least two, and I'm sure you see more than two. Now, Big Bang universes allegedly contain as many masses as you like, and radiation. All black hole universes are not expanding. As I mentioned, they're static. But all Big Bang universes are non-static. All black hole universes are asymptotically flat. Some really esoteric types are asymptotically curved, according to the cosmologists, but we won't be talking about any of them today. They're not worth it. But no Big Bang universe is asymptotically anything. Finally, all black hole universes, or no black hole universes, have a K curvature. And we've already seen that all Big Bang universes have a K curvature, one of three different values. So you see, you cannot put black hole universes into Big Bang universes, or vice versa. But what do the cosmologists do? They mix the two willy-nilly and get millions of black holes, billions of black holes. NASA's found 2.5 billion of them. The ESA just found one a couple of days ago in the Milky Way, not at the center, but revolving with another star. So they've got a binary black hole system. And all of this, of course, in a Big Bang universe. Which one, they don't tell us. They never tell which black hole either, because there are four types, you might recall from a previous talk that I gave. So we'll now move on to baking cake number 2. Black holes have a very schizophrenic property. Right? They have and do not have an escape velocity simultaneously at the same place. Now, no cosmologist understands what escape velocity means. I've mentioned this in detail in my previous talk, but this is a recap today. So that's a problem. Nothing has an escape velocity and no escape velocity simultaneous at the same place. But that's exactly what the black hole event horizon has. In fact, they tell us at the black hole event horizon, the escape velocity or the escape speed of a black hole at the event horizon is the speed of light. That's why nothing can escape. Really? If the speed of light if light is traveling at the speed of light and that's the escape speed, wouldn't you expect light to escape? I would. Let's continue. X is a black hole universe and Y is a Big Bang universe. X plus Y is not a universe. Neither is X plus X or Y plus Y. Why? Because general relativity is a nonlinear theory. You can't just add these together like solutions in simple equations and add them together. You can't do that because it's a nonlinear theory. Here's a simple graphics example of black holes. According to general relativity, or the cosmologist, every black hole has infinite curvature at its singularity. Well, if it has infinite curvature at every singularity, that's gravity. Gravity is not a force in general relativity, it's space-time curvature. So they're telling us that at each one of these black holes, see them in that little drawing there, each one of them has infinite curvature at its center, its so-called singularity. However, does any one of those have asymptotic flatness? Well, you go from one black hole to another one, and what do you encounter? Infinite gravity. You go from another one to another one, infinite gravity. Every black hole encounters infinite gravity at every other black hole. That's not asymptotically anything, and that violates the definition of a black hole universe. It's supposed to be asymptotically flat at the very least, so it's nonsense. Now we get into a little bit of mathematics. We're up to baking a cake 4.1. Whose cake are we baking? Well, the cosmologist's cake and Einstein's cake, and I think they'd really like to have a file in it somewhere. I'm not going to give them the privilege. Okay, general relativity, well, these are the equations of Einstein. Now, all you really need to do here is to identify parts.
G, what's that? This big G thing? It's the Einstein tensor. The R thing there with the arrow there, R sub UV, this is the Ricci tensor. R on its own is derived from the Ricci tensor and it's called the Ricci scalar. And G, this is an important thing called the metric tensor. It's sometimes called the fundamental tensor. We'll talk about metrics. And lambda is the cosmological constant. And T is the energy momentum tensor. That's it. We've identified all the parts. But what do they mean? Well, the energy momentum tensor is supposed to describe all the material sources of Einstein's gravitational field. And the G is supposed to describe the geometry, because matter causes space-time to curve. So the matter's on the right side, making the space-time geometry on the left side curve. That's gravity, according to Einstein. And the cosmological constant, what is that? Cosmologists don't really know. Einstein didn't really know. It's a fudge factor. Here's an interesting thing. Static and in the absence of matter. According to Einstein, when the energy momentum tensor, which we saw in the previous slide, is 0, his equation is reduced to this thing. The Ricci tensor equals 0. Well, according to Einstein, this describes a gravitational field of a body, or outside a body, such as a star. But this is circular reasoning. First, he removes all matter by setting the energy momentum tensor to 0. There are no material sources. Then, by going in a circle, he comes back and says, this describes a gravitational field outside a body. He just put it back in. Right? Now, some people will object to that. Oh, Crothers doesn't know what he's talking about. He's on the wrong trail. Well, really, here we can now prove the argument is circular. Because we take de Sitter's universe, it's described by this second equation, R equals lambda G. Well, according to the cosmologists and Einstein, this universe is empty. It's de Sitter's empty universe, right? It's empty because it doesn't contain anything. Why doesn't it contain anything? Because the energy momentum tensor is 0, just like the one beforehand. So according to Einstein and his followers, matter is both present and absent by the very same mathematical constraint. Do you think that's possible? I don't. It's not possible. So R, or the Ricci tensor equals 0, that universe, if it's a universe, it's as empty as de Sitter's universe for the very same reason. There are no material sources present. It's a contradiction. So that really bakes Einstein's cake completely. I'll have more to say on this later, because that means that setting the Ricci tensor to 0 is physically meaningless. It has nothing to do with physics. Now we come to a little bit of numerology. This is the so-called Schwarzschild solution, but it's Hilbert's version, and it's a magic trick by Hilbert. In this expression, C equals G equals 1. What's C? It's the speed of light. G is Newton's gravitational constant. And they set them to 1, so they disappear out of the equations. And they claim that this little m in this equation is the mass of that's the source of the gravitational field that Einstein says Rick equals 0 to. This is the mysterious mass that is taken out and put back in. Let's see how they insinuate Newton into this expression. Let's put C and G in explicitly. Now, Hilbert's expression becomes this. C and G are now present, because if you make C and G 1, we get Hilbert's 2m over r. And notice that they want r to go down to 0. This gives them their two so-called singularities. One, they say they can remove the event horizon of their black hole, because when r is equal to this so-called Schwarzschild radius, they call it a radius, and they give it a value, 2gm over c squared. Again, if g and c are 1, you have r equals 2m. And if you put that into that expression there, you find that the second term with the power to the minus 1 becomes 1 over 0. Right? Well, that's undefined, and they call that the event horizon. Then they put in r equals 0, because they want r to go down to 0. They think it's the radius. And they put in 0, and then the first term gets what? 1 over 0 as well. Now notice, if we rearrange this so-called Schwarzschild equation, or Schwarzschild radius rather, for c, we get c equals the square root of 2gm over r. Well, we recognize that immediately as Newton's expression for escape speed. The thing about this, of course, is that Newton's expression for escape speed pertains to two bodies. You have to have at least two bodies, because one escapes from another one. Just because one mass is missing from this equation doesn't mean it's not implicitly present. Because if you have two things, one escapes from the other. And this describes what speed is the necessary minimum for one body to escape from another body when the body that you're referring to has mass m. So by this expression, they have two things: a radius of the event horizon of a black hole, and 2, the escape speed of the black hole. That's why they tell you that the escape speed at the event horizon is the speed of light. They got it from Newton's expression. How can you put a two-body relation in what's allegedly a solution to a one-body problem? You can't. Here's some further confusion. This is what I call scientific or delusional science. Right? Delusional science. Cosmologists in confusion. What do they think Hilbert's R is? We saw that expression. I've given a list here. They think it's the areal radius, the coordinate radius, the radius. A guy with a Nobel Prize called Gerardus Tourf tells us this. It's the radius. He tells us also it's the distance, so do many others. He tells us it's the radial coordinate, so do many others. It's the radius of a two-sphere, the reduced circumference, the radial space coordinate. And here's my favourite one of all. A gauge choice, it defines the coordinate R. You know? I could call this Fred Flintstone, or I could call it dark matter, or I could call it doesn't matter. It doesn't matter. Because all of them are wrong. Now we'll come to a little bit of surface theory to see why their mathematics is so false. This is a simple expression. It's called the first fundamental quadratic form for a surface. Now the g's, they're functions of two variables, u and v. U and v are the only variables, and you see here that we have a number of terms, GUU, GUV, GVV. Well, GUV is equal to GVU, so that's why it appears twice. But how many variables are there? Two, because it's a surface. Surfaces have only two variables, two dimensions. The area from Gauss's surface theory is given by, or an element of area is given by the second expression. This is an element of area. You would have to integrate that to get the full area over the range for the domain for values of u and v as required. Now, if u and v are functions of another parameter, we'll call it t. But just because I call it t doesn't mean it's time. I could put in Fred Flintstone. U is a function of Fred Flintstone. I could stick it in there, and then I get now an element of length. Anywhere in the surface, I can calculate length between 2 points in that surface by this parameterized expression. T is the parameter. It doesn't matter what you call it, it's just a dummy variable. Metric tensors. This is a lot of things that cosmologists hide behind. Most of them don't even understand it. They say, oh, well, that's a tensor. Really? What's a tensor? Most of them don't even know that. But they use it nonetheless. Oh, I'll go and read a textbook. The metric tensor. Well, we saw before that we had G, U, V. Well, we can have G11, G12, G21, G22. That covers the whole four of them. Remember, we had four of them. The first one, the two are in the middle, and the third one, because it's a surface. There are only four components here. And so we can write them together in a matrix like this, and we call this the metric tensor. And the determinant of this metric tensor, well, we just take the determinant. Theory of determinants, we take the determinant of this. It's pretty straightforward. So G will represent the determinant. The GUV, we can write it as a matrix, and we'll call the GUV now the metric tensor. But what's a metric? They sometimes call it a line element. What's a line element? It's nothing other than fancy names for a distance formula. What's the distance between these 2 points? Give me the formula. How do you calculate it? Give me the formula. In elementary algebra or linear analytic geometry, you learn that in, year 10. You've got 2 points, x1, y1, x2, y2. What's the difference? The distance between them. You apply the theorem of Pythagoras and you get a distance. Now we do it in little bits. You get a line element. It's a distance formula. That's all it is. So let's have a look particularly at a distance formula. Okay. We want to now calculate a thing called Gaussian curvature, because this will identify what R is in Hilbert's metric. And then we'll see whether or not it can go down to zero. I'm going to show you that it can't go down to zero. And because of that, everything about black holes is immediately destroyed. The intrinsic geometry of a surface is completely independent of any embedding space. So if you take the surface, it's two-dimensional, you stick it in a three-dimensional space, it doesn't matter what kind of space, the intrinsic geometry of the surface is unaltered. In other words, we can talk about the intrinsic geometry of the surface with total disregard to any embedding space. We don't need it. Gauss proved that. Now, in the surface in Hilbert's solution, Hilbert's metric, is this one, ds squared. We see there are only two variables, theta and phi. R is not a variable here. There's no dr. R is a fixed quantity. You can assign it some value. Now, if we calculate the Gaussian curvature of a surface, we can do this by using K equals 1 over R1212 over G. G, we saw before, is the determinant of the metric tensor, and R is what? This is a component of the Riemann tensor of the first kind. We won't get into that. All you need to know is that's what it is. And what's G? Well, we see in this case, G11 is what? It's R squared. G1221 is 0, because it doesn't appear. and G, 2, that's r squared sine squared theta. They're the coefficients of the variables. How do we calculate this? Well, we have to calculate by using we can do it in a number of ways, but here's a simpler way. Now, I'll just go back for a moment. If you look at this metric tensor, you see that you've got r squared in the top left corner and r squared sine squared theta in the right corner. That's a diagonal. If there's zeros everywhere else and not on the diagonal, this is called a diagonal matrix. So we can say that this metric tensor is diagonal. It's mathematical jargon. Now, in the case of tensors that are diagonal, we can use these simple relations to calculate Gaussian curvature. The top equation gives us the Riemann tensor of the second kind, and the second equation tells us how we get from that the Riemann tensor of the first kind, and we want the 1, 2, 1, 2 bit that we saw before. Now, to calculate these other things, these gamma symbols, these are called Riemann-Christoffel symbols, and they're complicated things, but to calculate them, we have these two relations. Now, if you do all of those calculations, the result that we want, the result that we want to concentrate is the bottom one. We get the Gaussian curvature is 1 over r squared. So now we have an identity of what r is in Hilbert's metric. It's none of those things that those cosmologists talk about. R is what? It's related to the Gaussian curvature, and in this case, it's the inverse square root of the Gaussian curvature of the surface. The surface geometry, of course, is independent of any embedding space. So you stick the surface into an embedding space, that's not going to change its identity. What's the real radius in Hilbert's metric? We make a calculation. We integrate the term that contains dr, and then we get this expression by evaluating the constant. I put the constant in, and we get the square root of alpha in the second term. Now, notice something about here. When r equals alpha, and in the case of Hilbert, he assigns alpha to gm over c squared, and then he makes c and g 1. Well, rp is 0. That's the radius. So that means when r equals alpha, or 2gm over c squared in the case of Hilbert, this equation is 0. The radial distance is 0. So that means that's where the origin of this geometry is located, and there is no possibility for r going less than 0. We look at Minkowski's metric. This is this metric for special relativity, flat space-time. It goes down to r equals 0. We calculate the radius, and we get rp equals r. They're identical. We go back to the other one. Does rp equal r there? No, because it's a non-Euclidean geometry. So I calculate the radius, it's a different thing. So in this case, the Gaussian curvature and the radius r are directly related in this form. R is 1 over r squared as a Gaussian curvature, and r is also the radius, because by calculation I get that. Why? Because it's a Euclidean space. The other one is a non-Euclidean space, so they don't have the same relation. So the Gaussian curvature is 1 over r squared. Let's look at Schwarzschild's solution. It looks like Hilbert's. In this case, Schwarzschild's r goes down to 0. But when r equals 0, little r equals 0, what about his big R? His big R equals alpha, the very constant I've been talking about, right? Hilbert's solution is therefore not equivalent to Schwarzschild's, because if it was, that would make Schwarzschild's big R have to go down to minus alpha, but it can't. It's defined in terms of r greater than or equal to 0. Let's have a look at Droster's solution. This looks exactly like Hilbert's solution, except it's got an alpha rather than 2m. And alpha is less than or equal to r. Again, here C is 1. And we'll have a comparison with Brillouin's solution. Brillouin wrote this equation in 1923, and you see in his case, r goes down to 0. But r is now kind of acting like a parameter. ds squared is this one, r goes down to 0. What do you find? These two are equivalent. And they're equivalent to Schwarzschild's. Because when Schwarzschild's little r equals 0, that's the same as when Droster's little r is equal to alpha, and the same as when Brillouin's little r is equal to 0. They all come out the same, and they produce the radius being 0. What the cosmologists want to do, they want to take Droster's solution where alpha is less than or equal to r and make r go down to 0. Why? Because they think it's the radius. We've already seen that it's not so. And they want to make the r equals 0 the origin of their geometry, but that's not so. Let's have a look at the Schwarzschild ground form. This is something that I wrote down in about 2005, in my first paper on this subject. Have a look at this equation, particularly RC. Now we see here, n is any positive real number, and r is any real number. So is r0, any real number. r0 and n are only arbitrary constants. You can pick what you like. But notice something. When r equals r sub 0, the radius that I calculated before is always 0, and is independent of the value of n and r, 0. Completely independent. That's what you want, independence of coordinates. So you see that RC is equal to alpha, and Rp of R sub 0 is equal to 0 for all values of R naught and all values of n. Let's take some examples. If I set R naught equals 0 and n equals 3, and I take R greater than R naught like Schwarzschild did, we get Schwarzschild's solution. If I set n equals 1 and R naught equals alpha and R is greater than R naught, I get Drosta's solution. If I set n equals 1 and R naught equals 0, I get R, and we take R in greater than R naught, I get Brillouin's solution. These equations are equivalent. It's saying the same thing with just some different symbols, but they're exactly the same geometrically. So the question is, can Drosta's solution be extended down to naught to get Hilbert's solution and generate a black hole? Now we talk about metric extensions. Now, I'm going to show you here, if you couldn't see that you can't do that, let's take a specific example. Let R naught equal 0 in that equation for RC, and let n equal 2. What do we get? This expression, and RC is equal to R squared plus alpha squared, and you take the square root of that. Well, R squared is R is a real number, and you square the real number, you get another real number. But the difference is, this squared real number is always greater than or equal to naught. Can R squared take minus alpha? Can R squared be minus alpha? It cannot. Now, since this expression generates Schwarzschild's solution, Drosta's solution, Brillouin's solution, any number of solutions you like, and they're all equivalent, if any one of that infinite equivalence class can be extendable to make Hilbert's black hole, in other words, to make Drosta's solution go down to naught, then every single one of them must be on account of equivalence. Alternatively, or conversely, if any one of those cannot be made to go down to RC equals naught, capital RC equals 0, then none can on account of equivalence. Well, if I make, you look at this one, can R squared take values of minus alpha and make RC sub 0 naught? It cannot. So we don't need homeomorphisms, we don't need diffeomorphisms, we don't need Hausdorff spaces, we don't need topological spaces. This completely ruins the black hole with simple mathematics. You cannot, because it's an equivalence class.
Okay, we had Steve Carruthers there ripping apart, shall we say, the accepted maths underlying a lot of the assumptions of relativity. I don't know that necessarily destroys it completely as a principle, but it certainly does a remarkable job of removing some of the wilder assumptions of it. I think I'm seeing an awful lot of credible arguments against a lot of the fundamentals in relativistic mechanics. Anyway, moving on, we're now going to step away from both quantum mechanics and relativistic mechanics, broadly speaking. We've got Rupert Sheldrake up next, discussing the nature of the belief that many things in science have been settled already. So here we go, Rupert Sheldrake with The Science Delusion.
The science delusion is the belief that science already understands the nature of reality in principle, leaving only the details to be filled in. This is a very widespread belief in our society. It's the kind of belief system of people who say, I don't believe in God, I believe in science. It's a belief system which has now been spread to the entire world. But there's a conflict in the heart of science between science as a method of inquiry based on reason, evidence, hypothesis, and collective investigation, and science as a belief system or a worldview. And unfortunately, the worldview aspect of science has come to inhibit and constrict the free inquiry, which is the very lifeblood of the scientific endeavor. Since the late 19th century, science has been conducted under the aspect of a belief system or worldview, which is essentially that of materialism, philosophical materialism. And the sciences are now wholly owned subsidiaries of the materialist worldview. I think that as we break out of it, the sciences will be regenerated. What I do in my book, The Science Delusion, which is called Science Set Free in the United States, is take the 10 dogmas or assumptions of science and turn them into questions, seeing how well they stand up if you look at them scientifically. None of them stand up very well. What I'm going to do is first run through what these 10 dogmas are, and then I'll only have time to discuss one or two of them in a bit more detail. But essentially, the 10 dogmas, which are the default worldview of most educated people all over the world, are first that nature is mechanical or machine-like. The universe is like a machine, animals and plants are like machines, we're like machines. In fact, we are machines. We're lumbering robots, in Richard Dawkins' vivid phrase, with brains that are genetically programmed computers. Second, matter is unconscious. The whole universe is made up of unconscious matter. There's no consciousness in stars, in galaxies, in planets, in animals, in plants, and there ought not to be any in us either, if this theory is true. So a lot of the philosophy of mind over the last 100 years is trying to prove that we're not really conscious at all. So the matter's unconscious, then the laws of nature are fixed. This is dogma 3. The laws of nature are the same now as they were at the time of the Big Bang, and they'll be the same forever. Not just the laws, but the constants of nature are fixed, which is why they're called constants. Dogma 4, the total amount of matter and energy is always the same. It never changes in total quantity, except at the moment of the Big Bang, when it all sprang into existence from nowhere in a single instant. The 5th dogma is that nature is purposeless. There are no purposes in all nature, and the evolutionary process has no purpose or direction. Dogma 6, biological heredity is material. Everything you inherit is in your genes, or in epigenetic modifications of the genes, or in cytoplasmic inheritance. It's material. Dogma 7, memories are stored inside your brain as material traces. Somehow everything you remember is in your brain in modified nerve endings, phosphorylated proteins. No one knows how it works, but nevertheless, almost everyone in the scientific world believes it must be in the brain. Dogma 8, your mind is inside your head. All your consciousness is the activity of your brain and nothing more. Dogma 9, which follows from dogma 8, psychic phenomena like telepathy are impossible. Your thoughts and intentions cannot have any effect at a distance because your mind's inside your head. Therefore, all the apparent evidence for telepathy and other psychic phenomena is illusory. People believe these things happen, but it's just because they don't know enough about statistics, or they're deceived by coincidences, or it's wishful thinking. And dogma 10, mechanistic medicine is the only kind that really works. That's why governments only fund research into mechanistic medicine and ignore complementary and alternative therapies. Those can't possibly really work because they're not mechanistic. They may appear to work because people would have got better anyway, or because of the placebo effect. But the only kind that really works is mechanistic medicine. Well, this is the default worldview, which is held by almost all educated people all over the world. It's the basis of the educational system, the National Health Service, the Medical Research Council, governments, and it's just the default worldview of educated people. But I think every one of these dogmas is very, very questionable. And when you look at it, they fall apart. I'm going to take first the idea that the laws of nature are fixed. This is a hangover from an older worldview before the 1960s, when the Big Bang theory came in. People thought that the whole universe was eternal, governed by eternal mathematical laws. When the Big Bang came in, then that assumption continued, even though the Big Bang revealed a universe that's radically evolutionary, about 14 billion years old, growing and developing and evolving for 14 billion years, growing and cooling, and more structures and patterns appear within it. But the idea is all the laws of nature were completely fixed at the moment of the Big Bang, like a cosmic Napoleonic code. As my friend Terence McKenna used to say, modern science is based on the principle, give us one free miracle and we'll explain the rest. And the one free miracle is the appearance of all the matter and energy in the universe and all the laws that govern it from nothing in a single instant. Well, in an evolutionary universe, why shouldn't the laws themselves evolve? After all, human laws do, and the idea of laws of nature is based on a metaphor with human laws. It's a very anthropocentric metaphor. Only humans have laws. In fact, only civilized societies have laws. As C.S. Lewis once said, to say that a stone falls to earth because it's obeying a law makes it a man and even a citizen. It's a metaphor that we've got so used to, we forget it's a metaphor. In an evolving universe, I think a much better idea is the idea of habits. I think the habits of nature evolve. The regularities of nature are essentially habitual. This was an idea put forward at the beginning of the 20th century by the American philosopher C.S. Peirce. And it's an idea which various other philosophers have entertained, and it's one which I myself have developed into a scientific hypothesis, the hypothesis of morphic resonance, which is the basis of these evolving habits. According to this hypothesis, everything in nature has a kind of collective memory. Resonance occurs on the basis of similarity. As a young giraffe embryo grows in its mother's womb, it tunes in to the morphic resonance of previous giraffes. It draws on that collective memory. It grows like a giraffe and it behaves like a giraffe because it's drawing on this collective memory. It has to have the right genes to make the right proteins, but genes, in my view, are grossly overrated. They only account for the proteins that the organism can make, not the shape or the form or the behavior. Every species has a kind of collective memory. Even crystals do. This theory predicts that if you make a new kind of crystal for the first time, the very first time you make it, it won't have an existing habit. But once it crystallizes, then the next time you make it, there'll be an influence from the first crystals to the second ones all over the world by morphic resonance. It'll crystallize a bit easier. The third time, there'll be an influence from the first and second crystals. There is, in fact, good evidence that new compounds get easier to crystallize all around the world, just as this theory would predict. It also predicts that if you train animals to learn a new trick, for example, rats learn a new trick in London, then all around the world, rats of the same breed should learn the same trick quicker just because the rats have learned it here. And surprisingly, there's already evidence that this actually happens. Anyway, that's my own hypothesis in a nutshell of morphic resonance. Everything depends on evolving habits, not on fixed laws. But I want to spend a few moments on the constants of nature too, because these are, again, assumed to be constant. Things like the gravitational constant, the speed of light, are called the fundamental constants. Are they really constant? Well, when I got interested in this question, I tried to find out. They're given in physics handbooks. Handbooks of physics list the existing fundamental constants, tell you their value. But I wanted to see if they'd changed, so I got the old volumes of physical handbooks. I went to the Patent Office Library here in London, and they're the only place I could find that kept the old volumes. Normally people throw them away when the new values come out. They throw away the old ones. When I did this, I found that the speed of light dropped between 1928 and 1945 by about 20 kilometers per second. It's a huge drop because they're given with errors of only fractions of decimal points of error. And yet, all over the world, it dropped, and they were all getting values very similar to each other with tiny errors. And then in 1945, it went up, 48, it went up again. And then people started getting very similar values again. I was very intrigued by this, and I couldn't make sense of it. So I went to see the head of metrology at the National Physical Laboratory in Teddington. Metrology is the science in which people measure constants. And I asked him about this. I said, what do you make of this drop in the speed of light between 1928 and 1945? And he said, oh dear, he said, you've uncovered the most embarrassing episode in the history of our science. So I said, well, could the speed of light have actually dropped? And that would have amazing implications if so. He said, no, of course it couldn't have actually dropped. It's a constant. So, well then how do you explain the fact everyone was finding it going much slower during that period? Is it because they were fudging their results to get what they thought other people should be getting, and the whole thing was just produced in the minds of physicists? He said, we don't like to use the word fudge. I said, well, what do you prefer? He said, well, we prefer to call it intellectual phase locking. So I said, well, if it was going on then, how can we be so sure it's not going on today? And that the present values are produced by intellectual phase locking. And he said, we know that's not the case. I said, how do we know? He said, we've solved the problem. And I said, well, how? He said, well, we fixed the speed of light by definition in 1972. So I said, but it might still change. He said, yes, but we'd never know it because we've defined the meter in terms of the speed of light. So the units had changed with it. So he looked very pleased about that. They'd fixed that problem. But I said, well, then what about big G, the gravitational constant known in the trade as big G? It's written with a capital G, Newton's universal gravitational constant. That's varied by more than 1.3% in recent years. And it seems to vary from place to place and from time to time. And he said, well, those are just errors. And unfortunately, there are quite big errors with big G. So I said, well, what if it's really changing? I mean, perhaps it is really changing. And then I looked at how they do it. What happens is they measure it in different labs. They get different values on different days, and then they average them. And then other labs around the world do the same, and they come out usually with a rather different average. And then the International Committee on Metrology meets every 10 years or so and average the ones from labs around the world to come up with the value of big G. But what if G were actually fluctuating? What if it changed? There's already evidence, actually, that it changes throughout the day and throughout the year. What if the Earth, as it moves through the galactic environment, went through patches of dark matter or other environmental factors that could alter it? Maybe they all change together. What if these errors are going up together and down together? For more than 10 years, I've been trying to persuade metrologists to look at the raw data. In fact, I'm now trying to persuade them to put it online on the internet with the dates and the actual measurements and see if they're correlated, to see if they're all up at one time, all down at another. If so, they might be fluctuating together, and that would tell us something very, very interesting. But no one has done this. They haven't done it because G is a constant. There's no point looking for changes. You see, here's a very simple example of where a dogmatic assumption actually inhibits inquiry. I myself think that the constants may vary quite considerably, within narrow limits, but they may all be varying. And I think the day will come when scientific journals like Nature have a weekly report on the constants, like stock market reports in newspapers. You know, this week, big G was slightly up, the charge on the electron was down, the speed of light held steady, and so on. That's one area, just one area where I think thinking less dogmatically could open things up. One of the biggest areas is the nature of the mind. This is the most unsolved problem, as Graham just said, that science simply can't deal with the fact we're conscious. And it can't deal with the fact that our thoughts don't seem to be inside our brains. Our experiences don't all seem to be inside our brain. Your image of me now doesn't seem to be inside your brain, yet the official view is there's a little Rupert somewhere inside your head, and everything else in this room is inside your head. Your experience is inside your brain. I'm suggesting actually that vision involves an outward projection of images. What you're seeing is in your mind, but not inside your head. Our minds are extended beyond our brains in the simplest act of perception. I think that we project out the images we're seeing, and these images touch what we're looking at. If I look at you from behind, you don't know I'm there. Could I affect you? Could you feel my gaze? There's a great deal of evidence that people can. The sense of being stared at is an extremely common experience, and recent experimental research suggests it's real. Animals seem to have it too. I think it probably evolved in the context of predator-prey relationships. Prey animals that could feel the gaze of a predator would survive better than those that couldn't. This would lead to a whole new way of thinking about ecological relationships between predators and prey, also about the extent of our minds. If we look at distant stars, I think our minds reach out in a sense to touch those stars and literally extend out over astronomical distances. They're not just inside our heads. Now, it may seem astonishing that this is a topic of debate in the 21st century. We know so little about our own minds that where our images are is a hot topic of debate within consciousness studies right now. I don't have time to deal with any more of these dogmas, but every single one of them is questionable. If one questions it, new forms of research, new possibilities open up. And I think as we question these dogmas that have held back science so long, science will undergo a reflowering, a renaissance. I'm a total believer in the importance of science. I've spent my whole life as a research scientist, my whole career. But I think by moving beyond these dogmas, it can be regenerated. Once again, it can become interesting and, I hope, life-affirming. Thank you.
The wonderful Rupert Sheldrake there, receiving a warm reception at the TEDx that he was speaking at there. It's not a popular stance to take in the modern world. We are given broadly simplified versions of the arguments that are still running currently through the various threads of science. And so what I've hopefully presented you with this evening is an outline of the experiments that led to the necessity for something such as quantum mechanics, the apparent inescapability of the conclusions that both the experimentalists and the theoreticians were deriving. It has been an incredibly powerful theory. Essentially, we wouldn't have the advances of the 21st century if it wasn't such a powerful theory. I think that we may be looking, broadly speaking, there at the power of the maths, which may be internally coherent without necessarily being quite as supportive of the theory as we are currently being led to believe. That said, we certainly have a lot to thank for the towering minds that have poured themselves onto this subject for a long time. And in conclusion tonight, I'm just going to present a short 15-minute audio of somebody opening up the subject a little more. Again, it's quite a technical piece, but hopefully, I'm afraid the audio, I suspect English is not this chap's first language. The audio is quite difficult to listen to, but I would recommend that you endeavour to stay with it. I'll be back to say goodbye after that.
The Danish scientist Hans Christian Ørsted rediscovered in 1820 the effect of electrical current on magnets. This effect was first discovered by Gian Domenico Romagnosi in 1802. The compass needle is deviated by the electrical current in the wire. Andrew Murray Ampere in 1827 explains the Ersted's experiment by his theory of molecular flow. Countless minute particles electrically charged would be moving in the conductor. He attributes the electric current the opposite direction of the flow of electrons discovered in the late 19th century. In 1875, the American physicist Rowland discovered that a rotating electrically charged disk has a magnetic field. These two experiments seem to prove that the magnetic field is a result of electron translation. Is that true? It was concluded that the electron intrinsic magnetic field would result from the rotation of the electron charge, which does have a dipole structure, although there is not the slightest experimental evidence. Is that true? The Clements experiment is intended to show it is not in both cases. The magnetic field of a cathode ray is measured before and after a 90 degrees bend obtained first by an electrical field. Is there a magnetic field after the bend? This is the Clements experiment principle. The translation of the electrons is not the cause of the magnetic field, and the structure of the electron field is rotational. While waiting for the experimental result, it can be noted that with the standard model of the electron we are led to two potential causes of the magnetic field. On the one hand, the displacement of the electrons, and on the other hand, the intrinsic magnetic moment. The situation is contrary to the principle of simplicity, the famous Occam's razor. Since the intrinsic magnetic moment of the standard model would result from the translation of electrons, the only solution to this paradox is to waive the translation. The rotational magnetic field of the electron is the sole cause of the magnetic field both of the electrical currents and of the cathode rays. The rotational structure of the electron field is to be compared to the link between the magnetic field and the angular momentum of the electrons. As a consequence, the magnetic field of the electrons cannot be directly the cause of the magnet fields. It is necessary that the electrons are organized into ring structures in the matter of magnets. Electrons of magnets include, and such structures generate a magnetic field similar to that of the magnets. Such a provision might allow envisaging a quantitative explanation of the Barnett effect by precession effect. In Barnett effect, the rotation of a magnet changes its magnetic field. The precession effect also explains the magnetic field of an electrically charged disk and rotation of the Rowland experiment. In both cases, the axis of rotation of the electrons is set precessing. This results in a mean magnetic field of electrons in the enforced axis of rotation. A consequence of the Clements experiment is that the Maxwell-Ampere equation is false. The magnetic field of an electric current is equal to the geometric sum of the magnetic moments of the electrons in the conductor. The second term of the second member of the equation makes no sense. Magnetic fields result exclusively from the magnetic fields of the electric charges. The magnetic fields which occur during charging of the capacitors results from the orientation of the electron field. Powering a conductor changes the electronic arrangement of the conductor and gives the magnetic field of the electrons an orientation collinear to the conductor. The electrons extracted from the cathode of the electron gun of the CRT by the anode voltage keep this orientation even after the elbow. Suppression of the displacement current invented by Maxwell to solve a mathematical divergence problem has another consequence. The Maxwell-Hertz equation makes no sense. If the waves of space result, in particular, from the electrons' vibrations, and if they have an effect on the electrons, there is no evidence they are electromagnetic in nature by themselves. By renouncing to this pure postulate of Maxwell, it can be envisaged to understand the results obtained by Professor Allais. Miller's measures with a Michelson interferometer are correlated to the respective positions of the Earth, the Sun and the Moon. So it is that Descartes was right. Gravitation and light are carried by the very same medium. This is the famous theory of whirls. Without going into the details of this theory, it should be noted that the theory of Descartes explains the Michelson's and Sagnac's experiments with full evidence. The most amazing is that Descartes had foreseen the deflection of light by the sun. Descartes' theory, however, raises three issues. The differential action imagined by Descartes does not conform to the law of Newton. By analogy with the whirl of the depressions of the atmosphere, it is likely that a condensation occurs also in space. If the middle of the space condenses in the nucleus of atoms, then the resulting flow has a velocity directed toward matter complying with the law of Newton. Additionally, the action of the stream on the nuclei of atoms is proportional to the mass of the nuclei if it has a bubble structure instead of a solid ball. It was then really Newton's law. Under the principle of Hamilton, the flow of a fluid towards a sink shall rotate and form a whirl. But then arises another difficulty: the speed of such whirls is inversely proportional to the distance to the center. The medium of the space has a special nature, since the tangential speed of planets is inversely proportional to the square root of that distance. The solution is simple. To obtain this law, it is sufficient that the particles of the medium of space be animated, not only with a Brownian agitation, as in all fluids, but also of an angular momentum. The principle of equipartition of energy doubles the energy term within Lagrange equations, which then the integral is the inverse of a square root. We can also notice that the energy of the particles of space has an interesting form. The medium of the space has a pressure as all fluids. This pressure acts on the nuclei of atoms and maintaining its cohesion. It can be likened to an ideal gas. A particle moving in this fluid is subjected to an overpressure upstream resulting from the increase of the mean square velocity of the particles in the medium of space and a depression downstream. Its lifetime is extended accordingly if it is unstable. A particle moving very fast in the medium of space is flattened so that its wavelength is changed in addition to the Doppler effect. In perfect fluids, the rotation of the fluid in the vortex compensates exactly the rotation of the fluid particles. This flow is irrotational. This does not occur in the medium of the space. The term energy is doubled. The whirl rotation requires an input of angular momentum. It can only come from the angular kinetic energy of particles of the medium of space. The whirl rotation speed absorbs a portion of the angular kinetic energy of the particles of the medium of space. So that, for example, near the Sun where the speed is very high, the law of tangential velocities is no more exactly the inverse of the square root of the distance. A similar phenomenon occurs for galaxies that do not comply with this law. Their size leads to a significant decrease of the angular kinetic energy available close to their eye, so that the speed of stars within galaxies is independent from their distance to the eye. The flattened shape of galaxies confirms an aspect of the theory of Descartes. We now know that the whirls are stable flows to well under the principle of Hamilton. If the condensation of medium space in matter has a spherical symmetry, the whirls have an axial symmetry. In application of the Poincare theorem, the whirl is concentrated in a plane that is the equatorial plane. On each side of the equatorial whirl, the medium of the space also condenses so that inverse whirls should appear and so on to the poles. These zones are separated by whirling cones giving to the zones alternating reverse rotations. This is what explains the zonal appearance of planets such as Jupiter, Saturn, Uranus and Neptune. Moreover, for the low inclinations, trajectories of comets calculated relative to the equatorial plane of the Sun have a clearly zonal distribution. This is also the case of ocean currents for the Earth. The phenomenon is also indisputable for terrestrial winds even if it is less clear. Finally, the rotation of the Sun on itself is essentially zonal. The issue of the quantified nature of light. If in viscous fluids, waves propagate in dispersing, it does not the same in a medium consisting of simple shape particles. The dispersion of waves in fluids derived from the complex form of molecules, and mainly of the hydrogen links in water. In the air, the sound is already much more directional. With a bullhorn, sound waves is concentrated. In the middle of the space, the vibrations of an electron causes two symmetrical wave trains whose cross-sectional area remains constant over very large distances if the particles of the medium are very regular spheres. In these conditions, they do not drag their neighbors. Such wave trains can therefore have effects similar to a corpuscle. It is the case of the photoelectric effect. The third problem is related to the transversal nature of light. The introduction of the angular momentum of the particles of space has an interesting consequence. Upon impact of these two particles, the momentum is transmitted according to the laws of Descartes. This transmission occurs by elastic deformation of the particles of space. But the angular momentum can only be transmitted transversally. This transmission results from the deformation of the particles, so there is no slip one against the other, as a result of flattening of contacting parts. This fact explains the transverse properties of the light. During oscillations of the electrons, they transmit their momentum to the heat particles of space, but also their angular momentum. Each wave train is polarized in the direction of the angular momentum of the emitting electron emitters. And of course the two symmetrical waves trains emitted during electron oscillation do have the same polarization state. This is the case of a blue sky in the opposite direction to the Sun and the double polarization of the case shell of the Sun observed with this instrumented tube with diaphragms. The Earth is dragged by the whirl of the Sun. It therefore does not move relative to the medium of the space. The light is supported by the same medium. The Michelson experiment therefore cannot highlight the movement of the Earth around the Sun, it uses light itself driven by the whirlwind. There is no need of the Lorentz transformation. Conversely, in the Sagnac experiment the disk carrying the mirror rotates relative to the middle of the space and its rotation can be detected. This is the principle of laser gyros. Professor Cellari was right. The Sagnac experiment contradicts relativity theory. The speed plays no part in magnetic fields. There is no problem of relativity within electromagnetic phenomena. There is no need of relativity theory. The speed of light is the quadratic mean of speeds of particles of space. The speed of light is not an absolute. There is no absolute in the experimental world. This approach obviously has countless other consequences. The galaxies do not rotate as required by the law of Newton. This is a result of the pumping of the angular momentum by the whirl. The tangential speed changes from 1 per square root of r to 1 per ram as in the red curve. It does not vary significantly over a long distance. There is no need of dark matter. Atomic nuclei grow with time. Seen at galactic distance, they must appear to us with a shifted spectrum. There is no need to assume that galaxies are receding from us to explain the Hubble effect. There is no need of the Big Bang. The planet's a higher density at the center than at the surface. The central part has to grow faster and the surface distend. There is no need to plate tectonics. The speed of condensation of the middle of the space is always much lower than the speed of light. There are no black holes. Contrary to corpuscles, waves in media may be divided into two wave trains and interfere. There is no need of the presence probability. The Orsay experiment, also known as Aspects experiment, poses no problem. The state of polarization is of course the same for the two symmetrical wave trains emitted by electrons. There is no need of quantum entanglement. Some phenomena related to light and gravity are explained in a quite elementary way, by the medium of space and the particles of space that compose it. But the mystery remains for the electric and magnetic fields. In the same way, all the problems related to particles remain unresolved.
And with that, I bid you thank you and good night. Thanks for staying with me on this. It's been an incredibly technical show. Really, really impressed with the listenership remaining to the bitter end. Play out with a few tunes till the hour. And see you again next week. Thanks, folks.
Why don't you want to do a version of Orange Claw Hammer live in the studio?
Yeah.